Welcome, everyone. Today we are covering this question: what's the time complexity of this particular computer program, algorithm, or piece of code? So let's read through it quickly. For int I is equal to 1 to n, for int j is equal to I star I, that's I squared to n, and then there's some piece of code inside which runs in constant time. So what's the time complexity of this particular computer program? So our first analysis could be that here there are two loops that nested. Maybe we can evaluate them independently and then just multiply. So let's try that first. So this is the outer loop. I is equal to 1 to n, order n. Simple, easy. Let's go to the inner loop. The inner loop goes from I star I squared to n. So, and I itself could be going from 1 to n. So if I is greater than equal to square root of n, then this loop just returns because it's for some higher value than n or greater than equal to n. So that runs in constant time, which we call O1. However, if I is equal to 1, then you're going to go from 1 to n, and this could take order n time. So generally, it takes n minus I star I time. Sometimes people say that it takes order square root of n time. That's not true. If I is equal to 1, then it's going to take order n time. If I is equal to 2, it's going to take order n time. I is equal to 3, it's going to take order n time. But as I becomes square root of n, then it starts taking order 1 time. And of course, it gradually decreases. So in worst case, it does take order n time. So if we multiply both the loops, we get order n for the first loop, order n for the second loop. And then we got big O of n square. That's not quite precise in this case. So we have to do better analysis. And here's the better approach. What we can do is we can break the outer loop counter. Instead of going from I to n, we first go from I is equal to 1 to square root of n. This is sometimes referred to as breakpoint analysis. So we have established square root of n as the breakpoint, and then we will still analyze the second part as well. But the first part here is I going from 1 to square root of n. The outer loop will then run square root of n time because going from 1 to square root of n. The inner loop never takes more than big O of n time anyway. So that leads to order n square root n times square root of n for this part. And then the outer loop does continue from square root n to n. And in that case, we know that the inner loop only takes order 1 time. The outer loop will run order of n time, well, n minus square root of n, which is order of n. So therefore, this takes order of n. Now, if we take the sum of these two, we have n times square root of n. So this is the better approach. Okay, let's summarize before we continue. Then we have a little bit more nuance that we still want to consider. But first of all, let's summarize that if we had simply analyzed both the loops independently, we would get n squared, but that's not quite right. So we introduced square root of n as the breakpoint, saying let's suppose the counter going from 1 to square root of n, then continuing from square root of n to n. In that case, this part of the loop only takes n square root of n time, and this takes n time. Therefore, in sum, it takes n square root of n time. So this is the better approach. Now, the nuance, the question that I was saying that we still have to address, we should still address is our analysis really tight? So we have shown that the given algorithm will not take more than n square root of n time. But is this analysis tight? Is the time complexity big O of n square root of n, or could it in fact be even lower? And why could it be lower? Because here we have still estimated this to be square root of n, but as you can imagine, when I starts getting close to square root of n, this actually doesn't even take that much time either. So could it be that our analysis is not actually tight? So to do the tightness analysis, we introduce another breakpoint. In this case, we are trying to estimate that the algorithm does not take less than this much time. So that's why we are using the big omega notation now. So let's break the counter I from 1 to square root of n divided by 2. And in this case, while the outer loop still only takes big omega of, in this case, the outer loop will take at least square root of n time because you're going from 1 to square root of n. However, the inner loop will start from n by 2 because as you recall, it goes from I square, which in this case will be n by 2 to n. So it runs in big omega of n time. Therefore, this part itself takes n square root of n time. And then there's more, you can analyze this further, but it's not really needed because you can see that this part of the algorithm already takes big omega of n square root of n time. So in total, we're going to get at least n square root of n time. And now we can put these two analyses together. We have shown that the time complexity of this algorithm will not be any more than n square root of n. And then we have shown that it won't be any less than n square root of n. Therefore, now we can say that the time complexity of this algorithm, this computer program, is theta n square root of n. So a little instructive lesson in how to use the breakpoint to be able to analyze some of these problems. That's all we have for you today. Have fun, keep learning.